Okay, good morning. It's actually morning for me, everybody. I'm going to go over the linearization and the tangent line approximation stuff we talked about in class. So go ahead and share the screen and get started. It's the notes we went over in class. I'm just going to fill them out again. So what we're going to do is we are going to go to our calculator. And the first thing we're going to do is turn off the lights so we don't get the reflection. Okay, so first thing we always do when we get a calculator, whenever we start a new question, is we're going to clear it. We do that with the second button. Plus 712. Second plus 712 clears your calculator. Okay, so now what I want to do is I want to go ahead and I want to graph this function, the square root of x, but I want to change my window. And the way you do that is the following. You go to the window button. We are going to change the x minimum to -1. We're going to change the x maximum to 6. We're going to change the y minimum to -1. Oh, that's the scale, clear. 1. We're going to change the y minimum to -1. We're going to change the y maximum to 3. Okay, so now we're going to put in our function the square root of x, second square root x. And what I want to do is I want to go ahead and graph that. So that's what our function looks like. It is a square root function. So what I want to do is I want to copy that over here. So the way I copy it over here is I need to get some good points. And if you think about it, the square root of 0 is 0. The square root of 1 is 1. The square root of 1, 2, 3, 4. The square root of 4 is 2. So what that gives us is it gives us a function that kind of looks like that. That's going to be our square root of x function. Okay, so now what I want to do is I want to zoom in when x is 4. So I'm going to hit the zoom button. I'm going to zoom in. And what I'm going to do is put this little target button. If I look down here at the bottom, I want to get when x is 4. So I'm going to zoom in here. I want to get to 4. Okay, it's pretty close to 4. I want to get it on the target itself or on the graph itself. So there we go. I'm going to hit enter. And what does that thing look like as I zoom in? If I actually zoom in that thing, it actually starting to appear to be almost a line. Even though it is a curved function, when I am here at 4, where it kind of has that curve, as I zoom in, it gets a line. And what I'm going to do is I'm going to zoom in again. So I'm going to do zoom, not Z-box, quit, graph. I'm going to zoom. I'm going to zoom in. And again, I want to have it right around 4. And zoom in. And as you see now, this thing basically becomes a line. So what we're going to be doing is we're going to be using our tangent line approximation to try and figure out values of functions. So what we are doing today is something called linearization. What it means is we are going to take a function, we're going to find the equation of the tangent line at a given point, and then we're going to use that equation to estimate values nearby. So let's go ahead and try and figure this out. I want to use the tangent line of f of x at f of x equals the square root of x at x equals 4 to approximate 4.1. So like what I'm actually trying to do is say, if I take the square root of 4.1, what does that equal? That's what I'm trying to figure out. So I'm going to use a tangent line approximation. So if you remember, this is our tangent line, y minus y1 equals m times x minus x1. So the things I need are the y1, the m, and the x1. So what I'm going to do is I can get this right here is going to be my x1 technically. That's my x1. I can get my y1 right from that. The f of 4 equals the square root of 4 equals 2. So that is going to be my y1 right there. So I got my x1 is 4, my y1 is 2. Now for slope, slope is derivative. So since f of x equals the square root of x, which is the same as x to the 1/2, the derivative is going to be 1/2 x to the -1/2. That is our expression that we can use to find the slope anywhere along the function. And we're actually going to look at this function here, f prime of 4. And that is going to be 1/2 4 to the -1/2. And I'm hoping at this point we start to realize what 4 to the -1/2 is. I'll do it over here. 4 to the -1/2 means 1 over 4 to the 1/2. Bring it down to the bottom. 4 to the 1/2 means this is 1 over the square root of 4. So this is 1/2. So this guy is equal to 1/2 times 1/2. This guy's equal to 1/4. There's our m. So our equation of the tangent line is y minus y1, which is 2, equals 1/4 x minus 4. And like from last unit, there's the equation of our tangent line. So I got like a flash of light behind me. What's going on there? So what I'm now going to do is I'm going to now use the tangent line to approximate this value. So what I'm going to do is I need to use this function or this equation, y minus 1/2 equals 1/4 x minus 4. What I'm actually going to do is I want to solve this for y. So I'm going to add 2 to both sides. And it's going to give me y equals 1/4 x minus 4 plus 2. And this is what I'm going to use to approximate this. So what I'm going to do is to get f of 4.1, that's an approximation. I'm going to use this function 1/4, 4.1 minus 4 plus 2. I'm going to simplify this guy out. So he's 1/4, 0.1 plus 2. 0.25 times 0.1 plus 2. This is going to give me 0.025 plus 2. So what I'm going to say is that this guy's approximation is going to be 2.025. So I'm approximating that the value of the function at f of 4.1 is 2.025. I'm now going to actually take the square root in the calculator. So what I'm going to do is second square root 4.1, 2.0248. So what it tells me is in my calculator, f of 4.1 actually equals the square root of 4.1, actually equals 2.0248. And if you look at these two numbers here, they're pretty darn close. What that means is I did a pretty good job of approximating, and that's what we do with approximation. This is what they did before calculators. Before calculators and computers existed, this is exactly how they would figure out values of functions. They'd say, hey, I know the value right here. Let's use it to find the value very close to it. So that's the idea, is we pick a value close to where we're looking, get a tangent line, then use the tangent line to approximate. Okay, so now approximations obviously are not exact. What we're going to talk about is we're going to talk about concavity. So when I talk about concavity, what I mean is the following. This right here is concave down. This right here is concave up. Again, concave down, concave up. 1 sec. Okay, go back to show the screen again. Sorry, took a break for a sec. Okay, so this is concave up, this is concave down. When we make our tangent line, if you remember what our tangent line is going to be, our tangent line is going to be a line that hits at one point. So what happens is we have a tangent line looks like that. Or we have a tangent line and the tangent line looks like that. So what we're going to find out is that when we are concave down, the tangent line, and if you look at it, where's the tangent line in relation to the curve? The tangent line is over it. The tangent line overestimates the actual value. When I look at a concave up, the tangent line is under it. So when we are a concave down, the tangent line, tangent line underestimates the actual value. And this is one of those things where you're either going to be told about it or eventually we're going to be able to determine it ourselves. So this is the next step. It's like when we do an approximation, we also have to say, is the approximation an over or an underestimate? Okay, so we're going to go ahead and do another example. This is a really nice one because if you look at this example, it's given us all the information we need to know. We need to be able to fill in this one, y minus y1 equals m times x minus x1. What's really nice? x1, y1, m, all given to us. So that tells me that the tangent line is going to be y minus a -3. So that's y plus 3 equals 4 times x minus 2. So to do my approximation, I'm going to move that 3 to the other side. So it's going to be 4 times x minus 2 minus 3. I'm not going to go ahead and do anything simplifying it. I'm just leave it alone. Because when I actually go to do this approximation of f of 1.9, it's actually easier to work with if I don't simplify it. So what I'm doing is I plugged in that 1.9 for x, and now I can just simplify. This is going to be 4 times negative 0.1 plus, or sorry, this is minus 3. Plus 3, minus 3. I'm going to make a mistake. Minus 3. So this is going to be negative 0.4 minus 3. This approximation tells me it's going to be negative 3.4. So the approximation for the value of 1.9 is going to be negative 3.4. Make sure you do the curly equal sign. That's approximation. If you do a hard equal sign like this thing over here, you're saying it is equal to it. It's not. It's an approximation. That's why we do that. So we know that this guy's concave up everywhere. So we then know that since he is concave up means we underestimated the actual value. So let's answer the question. The question says, is the estimate you found in part A greater or less than the actual value? So in this case, since we underestimated it, what we're saying is our value. What do we know? The estimate is the estimate. So is our estimate less than the real answer, or is it greater than the real answer? So in this case, since we underestimated it, our estimate is less than the actual value. And that is because the f of x is concave up. Okay. So again, we're going to walk through this, make sure we have all these questions answered. This is it for this topic. Next one, example 3, the radius of a circle is modeled by a twice differentiable function. If you think about twice differentiable is going to imply continuity. Actually, twice continuity. We're going to talk about something more about that later, but that's kind of an indicator for me. And what we have is we have time measured and we have radius measured. And what I need you to do is I need you to pay attention to the table, because the table is not x and y. The table is actually x or t and r prime of t. This entire row are slopes. Every one of those numbers is a slope. So given that r of 4 is 25, there's my x1, there's my y1. I need my slope. There's my slope at 4. That's going to be my m. So we're going to have y minus 25 equals 3.1 times x minus 4. That's my tangent line. That's my tangent line. I need to approximate 3.9. So what I'm trying to approximate is r of 3.9. And the way r of 3.9 is going to be is I'm going to use this function here, 3.1 times 3.9 minus 4 plus 25, because I moved the 25 over. And what's the really nice thing about this is in the world of FRQs, I just stop. Only thing I need to do is I need to talk about units of measure. I know that my units of measure here are listed as centimeters. So this guy is centimeters. The only thing I need you to be aware of, this isn't an acceptable form because it looks like centimeters goes with 25. Put a little pair of brackets around it. It's saying that number, when you simplify it, centimeters. So that's the answer. That would be the answer. You don't have to simplify it. If it was a multiple choice question, you would, but most likely you'd have the calculator to do it. Okay. And then the last one says it's concave down. Concave down implies overestimate. Is your estimate greater than or less than the true value? Because it's an overestimate, we're talking about a situation where it's greater than. Okay. So that is a linear approximation using the tangent line. Hopefully that helps. There was a homework, not many questions, but basically the same idea as working with graphs, tables, and actually the algebraic functions. So hopefully if you have any questions, come to the next class with them. Thanks.